Everyone, I am Suman Mojumdar, a postdoctoral research fellow. I am basically working in quantum computing, blockchain, security, and other fields. I am very much interested to work in linear section of varieties that is related to quantum entanglement and beyond. So I have selected a eminent topic that is basically published by Nathiel et al. And the title of this paper is Computing Linear Section of Varieties, Implication for Quantum Entanglement and Others Related Activities. This is already published in 2023 in a reputed IEEE journal. This is 64th Annual Symposium of Foundation of Computer Science that is called FOX. This is the coverage of my topic. Uh, so introduction. Uh, in this scheme, the authors tries to propose different conic varieties, though those intersects a flat surface or linear surface. So, what is conic variety? I am going to discuss in details for the subsequent slides, but I will give a brief introduction. The conic variety is a type of cone. If we consider a cone and we intersect the cone with some straight lines or some section, then the cut section of this cone that can be considered as a state space of a vector. We already know that vector have some magnitude and direction. The cutting space of the cone can be considered as a vector space. It is come from the concept that for the limitation of the vector space, which is cut and intersected by some polynomial like homogeneous polynomial, etc. Uh, this scheme shows the influence of quantum information theory and related to some complex mathematical problems like NP-hard, and the authors tries to decompose this higher term applications into some linear term or single one matrix or rank one matrix using tensor decomposition. I am also going to discuss the tensor and what is tensor decomposition procedure in the subsequent slides. But tensor can be considered as a DOA array for storing the vector data. And this scheme also the progress in quantum computing for better understand quantum entanglement complicated application. So quantum entanglement is basically use the concept of correlation between quantum bits based on some superposition of the quantum bits. This scheme also considers several subspace problem in quantum entanglement like R entanglement, complete entanglement, genuine entanglement of a vector subspace for some conic varieties. So and this scheme also tries to solve and all this actually this all type of means R entangle, complete entangle, and genuine entangle of the subspace are a type of NP-hard problem in worst case, and this scheme basically tries to solve these NP-hard problems in a polynomial time space for generic subspace and specific dimension. Um, what is R entanglement and the complete entanglement and all the cases? Actually, if we consider the V here is a vector space of the varieties in our sections, which can be intersected with a subspace U. So here U is the variety of a cut section under the vector V. So here V represent the quantum states, and here x1 is the cut section means cut variety, and it is cut from this variety is cut by the some conic section by some linear polynomial, and a subspace U can be intersected with this x1. So the cut section will be intersection of the x1 and subspace u is the generic subspace, and x is the cut section subspace of conic varieties. Our motto is to means the tries to maintain a rank. We can represent this cut section x1 of the conic variety, and tries to reduce into a linear term or rank one matrix. So x1 can be sorry, x1 has to be represented in a linear term rank one matrix, and the rank of the matrix is already discussed by the Summit scheme, where rank 1 is the simple term, and if we denote this section as xr, that means the rank of the matrix is less than equal to r. So in case of entanglement, there is the correlation between the quantum bits using the superposition is a combination of bits in a vector space or state space, and entanglement denotes the correlation between the superposition bits. So the cut section we have to be considered as a rank one matrix to to mitigate the NP hard problems. So if there is a possibility that the cut section contains a matrix with rank r less than equal to rank r, then the state space is a greater state space of entanglement states with a superposition with rank R matrix. So this is a superset of the x1 card variety of rank 1. So this type of xr contains the entanglement bits, means is a greater space of vectors. It is regarded as the R entanglement. So R entanglement related application can be, or it is a possibility that it is a NP hard problem. So we have to reduce these as a x1 means rank 1 linear matrix, which we can denote as the complete entanglement or genuine entanglement cases. So here are some background review is done by the authors. So first one is the Hirschman et al. Scheme. It is proposed in 1970. They basically used to tries to decompose the various vector space in a multimodal factor analysis using parafet decomposition, tensor decomposition procedure. So I'm going to discuss in subsequent slides the different procedure of tensor decomposition. So parafet is one of the tensor decomposition, and it is very old term. But this term contains some complexity, and it cannot guarantee that the tensor decomposition is being done properly. This technique is a very old and has limitation. To mitigate this limitation, Genrith et al. Has introduced a simultaneous diagonalization method. This is basically depends on the Hermitian operator. I am going to discuss the Hermitian operator, where the simultaneous diagonalization has been done using eigenvalues of the matrices, which basically decompose the high rank matrix into a smaller term. He tries to incorporate this diagonalization, simultaneous diagonalization procedure for decomposition of the tensor, using the same specific procedure, and his term this updated version of this term is specific parafet 1. But in this case, This scheme is limited with some type of tensor and may not cover all the scenario in high order tensor decomposition. Further, Lagrange et al. Proposed a decomposition method for three-way arrays, because we have already told that we can consider the tensor as a DOA array or any array. So he has considered the tensor as a three-way array, and accordingly he has decomposed this tensor with a complex structure, but this structure is not valid for any recent high order tensor decomposition, does not support. So this is a limitation. Ligon et al. Proposed some entanglement procedure and superposition related to quantum information theory. Mm, this study can work based on some specific stages of the vector space related to quantum entanglement. So this scheme has some limitation, has some barrier that does not support all type of quantum entanglement theories like R entanglement, complete entanglement, like these cases. Later on, Gour et al. Proposed an entanglement with superposition theorem with broader aspect of understanding the quantum states and their contribution in case of entanglement. But this is a very theoretical application, and this does not support in practical application scenarios. Later on, Bhaskar et al. Proposed a smooth decomposition procedure for tensor decomposition. This is a very robust technique, but this is works basically on certain condition of the certain condition of the tensor decomposition. Which is not supports all kinds of recent updated tensor decomposition methodologies. Later on, Barak et al. In 2016 proposed an entanglement technique for tensor decomposition with some procedure like sum of square or log-rank conjugate procedure. These are the procedure used for quantum decomposition for to make it very simple terms, but this procedures is very complex, reveals their complexity while computing related to means application space complexities. These are the several limitations we have means authors have faced, and this is a problem statement. Means the authors have faced some challenges regarding intersection of the conic varieties with linear subspace to get the vector spaces. So this is a recent challenge in quantum computing, where conic varieties is are intersected by a linear subspace. This is a recent problem. So considering this problem, one can take the vector space. This is a v the whole vector space, and among them we have some subspace has been chosen like u is the basis for like u1 u2 u1 are the basis for quantum states vectors, and an arbitrary conic section like x, which is cut by the homogeneous D polynomial. The polynomials are f1 to fp we have considered, and I have already discussed that while we done the intersection of this basis with u1 with x means the conic variety. Is it reveals zero or a non-zero point like vector point like v. If it is reveals zero, that means it reached the maximum term for such decomposition. Otherwise, there is some point or matrix that can be reduced. That has to be reduced actually to mitigate the NP-hard problems. So, using this procedure, the user has proceed using several algorithms. I am going to discuss in subsequent slides. So, these problems encapsulate a broader class of algorithm challenges that vary dependence on the choice of variety of the vector space. This can be a generic space or can be a complex vector space. I am going to discuss the several types of vector spaces. Uh, that can be basis steps or any complex steps. The particular case where variety comprises matrices of a bounded rank is deeply connected with fundamental issues such as quantum information theory and tensor decomposition. So, if there are any bounded rank in case of quantum decomposition, that is basically a very complex term in case of quantum decomposition nowadays, because we have to decompose this tensor in a linear term. So if there is a bounded rank, means there is a constant rank, so this can be a problem for making a linear term. So rank 1 matrix constitute a determinant variety which can so rank 1 matrix is produce a determinant variety, means it can be reduced using the determinants or matrices to mitigate the NP hat problems. So these are the problem statement of this scheme found by the author, and we have also found these problems. So there is a motivation of the authors. In this paper, the authors have motivated to design a generic or typical instance of the vector space for using some polynomial terms to cut the conic varieties and produce a linear term or simple term to mitigate the NP hat problems. So this is the motivation, and this is the motivation of this scheme. The means authors are motivated to design a novel scheme to mitigate such limitation. So what are the contribution of these authors in this scheme? The authors have investigate some insert of conic varieties. This is X. I have already discussed, which is a subspace of a vector space of means a conic variety with a linear subspace. So we have taken linear subspace as U, and the author tries to intersect the conic variety with the linear subspace with some homogeneous polynomials and with the cut section to get the varieties in a simple term or linear term from the complex term to linear term. So in the conic varieties, the author has chosen some close set, because to make there is a limitation for the space size of the space. This is basically we call non-degeneracy condition, which is followed by the authors, where some condition is imposed like the size of the vector space for the tensor decomposition cases. So this is some non-degeneracy condition proposed by the authors for the conic variety selection. Mm, and it is and in the quantum entanglement, low rank decomposition has been done. I have already told for the matrices with some simple term. The provides the authors provides a guarantee that the elements U means the linear subspace of the variety. I have already told that it maintains non-degeneracy assumption for this case. This scheme also consider the entanglement certification, means it is considered the full entanglement or the R entanglement kinds of things to mitigate the limitations, and it also consider unacceptable product basis. Unacceptable product basis is a term which is basically used for the status of the state space of the vectors in a means in a Hilbert space. Hilbert space is basically a space where several vectors spaces that can be generic space or any complex spaces reside. So the author consider the unacceptable product bias means to consider the state space in the Hilbert space. All the states are already valid state or not. For a state to be valid, they has to be the support the property of orthogonality, means the states application states can be orthogonal, means they are in a perpendicular nature in 90-degree angle, because we already know that vector has some value and magnitude. So they supports direction, so they has to support the orthogonality condition. The unacceptable product bias basically consider the orthogonality condition and the validity of the set spaces. Along with the quantum error connection course, means the general errors occurred at the time of quantum entanglement and superposition for the quantum bits. And I have already told this type of entanglement are entangled, completed, and consider the is NP hard case of algorithmic problems. So these are the several technical terms that has to be considered before going inside the scheme in details. Sorry. Uh, these are the some technical terms I will going to discuss in subsequent slides to better understanding for the scheme, because these all the technical terms are related to for the scheme. So here is some graphs is presenting the hardness of some application and along with the classical computers, means the easy application with the hard application. Here the graph showing that the simple term application like n term, this basically this graph is basically generated against the input size of the elements with the time or memory consumption. Like in a simple term n, the graph is some kinds of linear with x-axis, and in case of n log n term, this is all are simple terms that can supported by classical computers. So they produce the linear graphs against the input and consume input size has increased for these cases with respect to the others time, like polynomial term n squared. Here it is raised sharply against these simple terms. And in the second graph I am showing that the 5 to the power n term, this is the infinity type of application. So the graphs are increasing straightly here against the polynomial term. This is straight curve. If we increase further, we can this is basically the exponential term. 5 to the power n is basically the exponential term. The exponential raised sharply against the polynomial term and against the linear term. So this is the sharpness of the graph that reveals that for the small input size, the exponential term raised sharply along with the sharply against the means linear terms or polynomial terms. So this type of applications are hard applications or considered can be NP hard. And if we maximize the graph for better understanding, we can see the initial term. There is a significant growth. The polynomial term has a significant growth than the exponential term, but in later scenario, after some initial term, the exponential growth has significantly increased. Means that the initial case kinds of hard applications, the polynomial based applications are increased in a initial term, but later term the exponential growth has significantly increased. Means that the hard based application basically use the exponential term, and we have to reduce it into a polynomial term, and this type of applications cannot be supported by classical computers. Rather it can be supported by, as it is a hard problem, so it can be supported by the quantum computers. So this is the basic classification of the quantum classical computers with quantum computers. I am not going in details. I am just showing the summary. The quantum, the classical bits are deterministic 0 1. Quantum bits are probabilistic, means they support some k0 k1 term with some complex probability alpha and beta, where alpha and beta are the probabilistic term, where alpha square plus beta square is equal to 1 from the definition. And the classical computer support Boolean algebra, whereas the quantum computer supports linear algebra. Classical computer supports logic gates, logical operation which are irreversible, and quantum computer supports quantum gates. They basically works based on some Dirac notation, Kirchner bracket notation, or some matrix multiplication rotation, and all these applications are reversible. We can reverse the output from the input and input from the output. So the application of quantum computing is reversible. So the state space is deterministic, and the state space of the quantum computing is probabilistic. I have already told this one. So what is superposition? Superposition can be considered as a combination of bits with some probability. Means here the in quantum system the single qubit has been represented with some probabilistic term, like here k0 is the probability of 0 with alpha, and k1 is the probability of one of the bit with probability b. So this is called the superposition of bits with some probability. In case of quantum computing, this is the n term of the bit with some probability. So the state space and of the quantum classical computing is n, whereas the state space of the quantum computing is 2 to the power n. Means it is a hard problem. So we have to decrease the state space into some linear term to mitigate the hard applications into a simple term. This is the Dirac notation. Means there are two types of application in vector space. One is inner product and one is outer product. The inner product basically represents the probabilistic term of the vector space, like alpha beta. Where alpha square beta square is equal to 1. This is basically denotes the kinds of dot product, this is a inner product of the vector space, like kit 0 means 0 term represent a metric term 1 0, 1 is represented 0 1 with some probability. And this is the Dirac notation bracket. The bracket is also the same way. We can represent the output either in a bracket notation, means Dirac notation, or in a matrix representation format. And 0 and 1, ket 0 and 1 are the orthogonal basis term of the standard basis of a vector space. I have already told orthogonal basis. And Hilbert space is a complex two-dimensional space where the basis states are reside. So the every vector states of a vector is or in quantum computing are represented by a polarized term, where they maintains the orthogonality. Means one is horizontal term, and like 0 is horizontal and 1 is in vertical term with some probability. This is a general state with some probability. So they maintain some polarization of bits with some probability. So Ket0 and Ket1 are the basis terms, and there are some other states of quantum computing. These are the complex term of the states. 0 and 1 are the standard computational basis states of quantum computing, and there are other two states are also there, which basically denoted by the complex vector space. Those are Ket plus and Ket minus, and other are plus I and minus I. These all are orthogonal in complex states. So these are the also the state space in quantum computing. So now I have already discussed the representation of the state space can be done using to make it is in a simple term using Dirac notation or matrix representation, which is basically terms outer product. So we have to first done the vector space to represent in a basis transformation, means the superposition of bits. I have we have to first transform into a matrix or Dirac notation to make it applicable for every application and its simplicity. So this is the basis translation procedure in a outer product term. After that, the basis transformation is done, what already done, and we have to consider the linear transformation after that, because the basis term is the high order term. So we have to make the matrices from the high order term into a low order term, means rank 1 matrix, to make it in a linear term. So we have to done some linear transformation of the quantum system. Yeah, there are two procedures to make it using Hermitian operator or unary operator. Generally, both of the tools are used, but Hermitian is the very eminent application which is basically used, and we are also considering in this case the Hermitian operator, which is basically represented by H dagger, which is basically a complex conjugate transpose of a matrix with some eigen values, with some Hermitian matrix with real eigenvalues, and it follows the simultaneous diagonalization procedure to reduce the matrices. So I have already told that it follows all eigenvalues which all are reals, and the eigenvalues means eigenvalues forms the eigenvector space. This is the diagonalizable simultaneous diagonalizable procedure is follows, and all the basis states are orthogonal, means the eigenvectors are orthogonal in this case. So using this Hermitian operator or matrices with eigenvalues, we can decompose the tensor, or we can decompose the matrix using the simultaneous diagonalization procedure, which also here is showing the linear map version. I am going to discuss the linear map version in subsequent slide, which basically represents the maximal term of any vector space. So these are the conjugate Dirac notation. We are not going to consider here Dirac notation. We are going to represent only the matrix term in this application. So just I am giving an overview. The Dirac notation, there are two terms. One is Kate. These are the Kate term, and one is Bra. Bra. This is the Kate is basically a horizontal matrix, and Bra is basically a sorry. Kate is basically a column matrix, and Bra is basically a row matrix. Now with some conjugate terms. What is conjugate? Conjugate is basically here if we consider that alpha, this is alpha means the complex matrix A plus IB. So the conjugate of the alpha is the A minus IB. This is from the vector representation. This is basically used to represent the isomorphism of any vector space. So this is the notation. I am not going to in details. So orthogonal basis states can be represented by inner product. This is the probability. This is the okay. The single qubit state can be represented by Bose representation structure with some angle. This is not related to this, so going on details. And the multi-qubit system represented by cube sphere representation. This is basically a quantum circuit with some gates. This is Hadamard gate used for superposition. This is C not gate used for entanglement. These are the other gates for some basic structure, which is poly X gate, poly Z gate. I am not going in details. So linear transformation has been done using either bracket notation or matrix multiplication. It is showing that this is a bracket notation and this is a matrix multiplication procedure. And here are some example of basic gates. This is some Hadamard gate, and this is the notation of gates. So, what is tensor? We are interested in the term of tensor. Tensor is in mathematics. Tensor is an algebraic object that describes the multilinear relationship between the algebraic objects or any algebraic objects between the several algebraic objects in a vector space. So tensor is basically an object in a vector space. This can be considered as a states of the vector. Tensor represents a multi-dimensional array and like a container of the vector, like a container of the vector. This can be considered a space for containing the vector, means a vector space. So they can be considered as a matrix term, maybe several dimensional matrix. Here, this is a three-dimensional matrix, two-dimensional. This is the n-dimensional matrix. Sorry, d-dimensional matrix, which is a greater term, greater than three-dimensional cases. So we have to decompose tensor. Why we have to decompose the tensor? Because I'm going to in the subsequent slide. So regarding the complexity of the high order tensor means we face the complexity of the high order tensor while some kinds of application using vector spaces. So we need to decompose the vector from the higher term to the linear term, like from the DOA array to the singular matrix term. So we have to decompose this means tensor or DOA array into or the matrix into a linear matrix or rank one matrix. So tensor decomposition reduce the storage effort, allow an efficient computing during simulation process. There are four types of decomposition: canonic, polyadic, CP, which is basically the parafeg we have already shown in our background literature survey. So canonic, polyphase, tracker, tensor train, and hierarchical tracker decomposition. So two particular tensor decomposition technique is basically used maximally like for singular to decompose the tensor in a singular matrix or rank one matrix decomposition, and basically the candicom or parafec. This is basically a canonic decomposition procedure which is basically decompose the high order tensor into a sum of rank one tensor. This has a wide level of applicability nowadays for tensor decomposition, and another is tracker decomposition, which is also a high order form of principal component analysis. So we can consider tensor decomposition as a tool for data analysis and a mathematical tool to decompose the tensor as a sum of linear terms or rank one matrices. So these are the inventor of this decomposition procedure. This is the tensor decomposition procedure. I'm not going in details, but the overall terms. This is the high order tensor, and we have to decompose into a linear term. These are the several networks of the tensor, MPS or tracker network or TPS. These are the several structure which we have to be decomposed to make it a linear term. This is the MPS method for decomposing matrices. Um, um, this is the using the MPS procedure, which is basically used widely for decomposing the tensor, but it has some limitation, like the cost of this decomposition is x to the power 3 and memory usage x square. Why x square? Because this is a very important term. Why I have already told that while the rank of the tensor becomes the greater than 3, means it is a DOA tensor, there the complexity comes. Because here is a our motto is to decompose the matrix from d to the power n term to the power n d x square term, where this x is basically represent the tensor 10 rank for every decomposition. This every decomposition, though it is decomposed from d to the power n to the linear term, but the tensor 10 rank matrix is also increased in case of square term of the x. This is the x square term. So there is a complexity in case of matrix decomposition for the DOA matrices, where there is an open vector space. So these are the several way decomposition of matrices. There are the high order matrices. Sorry. So the rank one tensor means the vector output product, which is the matrix decomposition. This is our motto to decompose the tensor. This is the tensor decomposition procedure. This is the high order tensor to the single order matrix tensor. So these are the several procedures. This is here showing the single value decomposition method, which is also a CP method of decomposition with some simultaneous decomposition procedure of orthogonal matrices. This is showing that the orthogonal term with simultaneous decomposition of vector spaces. Here it is shown the simple term of this matrices with fewer elements, and in this case they have used the square term mid square methods. So this is a single term of generation for open spaces, and there are other methods for tensor decomposition like CP filtering, random matrix square, randomized matrix least square sub problems, or maximal likelihood problem, lineage CP. This is the lineage CP. This is the standard CPI. So the first one is the least square method. It reveals complexity. The first and second one, the least square method, it reveals complexity due to the n term. So with space complexity, so it is reduced by the randomized matrix square. But this is the randomized matrix square where the space complexity is considered. But there is another complexity. So it is simplified by the standard CP via maximum likelihood with probabilistic term. But it has some limitation complexity. So the some terms is reduced in the Rayleigh term to make it very lower space complexity, and subsequently Boolean CP is used using this probability term to reduce the space for open vector space application. So if we consider this is a complex circuit of a open vector space for the means for the circuit for the tensor. This is a complete tensor using some complex circuits. So now we have to decompose this complexity into a linear term. So there is a term called fidelity, which is basically measure the closeness of the two vector states between, means the correlation kinds of entanglement. This is fidelity is related to the entanglement, which is closeness or relationship, which is also in terms considered by the entanglement. So it is related. So while we decrease the matrix decomposition or matrix into high order to linear order, the fidelity also decreasing. Accordingly, based on the linear term, so correlation is decreased. So that means that the several errors has been decreased as with some linear term from the NP hard problem to the simple term. So here I am showing the decomposition procedure using the TBD algorithm, which is also a open space algorithm for decomposition of matrices with canonical decomposition. So the fidelity is showing that the fidelity is also decreasing while decomposing the um, decomposition the tensor or matrices. This is the fidelity decreasing. Yes, we have already tell that if the number of qubits is increased, means the open vector space, if it increase the circuit depth, means complexity is also increased. It refers the NP hard case if the qubit is increased. So in case of high rank tensor decomposition, we have already told that the X term is double for every layer. I have shown in the previous slides where the this X term is bond dimension. X term is the bond dimension doubles in every layer for decomposition. So if there is any complex circuit, so we can decompose up to 10 layers. Means we can decompose up to any layer, but it cannot work perfectly. Means the with high level of means fidelity, we can decompose up to 2 to the power 10 term, and this term the bond dimension becomes 1024 at the 10th level. So this is a high level of space complexity problem comes in the open decomposition methodologies. In case of 1D decomposition, there are 99% fidelity rate, and while 2D decomposition, this is 96% fidelity rate. The fidelity rate is decreasing, but the memory consumption is increasing due to bond dimension. So here is we are showing that in TBT, this is a green one, this is the open simulation, and this is a closed simulation. Closed simulation is decreasing the bond dimension. So we have to consider some closed simulation methodologies or closed vector space to deactivate some terms of this, like here one is the active matrices, and zero are the invalid vector space. So we have to consider some closed vector space application. So tensor product is the combining two matrices into a higher order, and then we decompose this matrix. So two matrices can be concatenated using tensor product, and further it is decomposed using tensor decomposition. As a tensor decomposition is basically a linear term, as a rank 1 matrix or in linear term. So, what is the span or correlation between tensor product and the span? We have several application use the term span. So, what is span? Span is basically the so sorry sorry the span. I'm going before going to the span. I'm going to why we use the tensor product, because in the vector space we cannot directly use the product term, means Cartesian product or kinds of applications, because due to commutative nature of the vector space, that allows the commutative nature cannot be supported by the product, like cross product, this cannot supported by the commutative properties of the vector. So we have to use the tensor product application to support the commutative properties for various field or ring, as we generally used in this case of application of vector space, where we use ring or field there. So we have to be supported this associative properties or commutative properties. So that's why we have to use the tensor decomposition methodologies. And using the tensor decomposition methodologies, there are two terms of the vector. One is the this is the vector size. One is the evaluation, means the matrix term in complex term, and one is the constant term. The matrix complex term is referred to as evaluation of a map, or the matrices. The evaluation is basically represents the maximal term of the matrix or linear term. So the sum of all the spaces of linear term of a vector is called the space of this vector, and the space of the vector is basically represented by the span, which is null term of the combination with the vector spaces, which is represented by nq, means the quotient. And there is a representation of the representation with the evaluation term with the quotient term as a tensor matrix, as a tensor multiplication term. So actually this property is used in case of linear map matrices to represent the maximum term. So this is the linear map matrices. We represent linear map to represent the commutative properties or associated properties of the field or ring. Like here we represent alpha dot beta is like this map represents the maximum term where there is a simple term like u cross v. This is represented in a linear matrix. This is the w linear map. This is w. So this matrix is basically imposed in a linear map where all the vector values are presented in this way. So this is the so here alpha is the whole term where a subpart of this matrix called W, where W is also a linear map with the vector space or subspace of the whole space. This is small u and v. And we have already told that the application of this quantum computing supports the inverse operation, or so that's why the w is a u tensor v product can also be supported by u tensor v that relates to w. So this is the inverse term, and this property is used in map to represent the isomorphism properties. So here it is showing that the sub part of a matrix which is also be represented using some linear map where the subspace can represent a maximal term, because maximum term is the subspace of the whole subspace of the whole vector space. So subset of a whole vector space which maintains the maximality condition, because the quotient or the subspace because the quotient of the subspace of the matrix represent the here I'm showing that this is the whole vector space u cross v to w is a linear mapping, but if we use the quotient or subspace vector like here q, the q is represent, this is the quotient nq, this is the span of this matrix. So if we divide this term, this is the quotient term q. It also represent a term called beta, which also generate the same vector space, but with maximal term with quotient, which means the subspaces. So here alpha and beta are, if we consider the subspace, then the associated property for the identity means the conic section varieties of a linear map that we have to be selected, means the identity ideal, sorry, identity not, this is ideal. Ideal means the space of the vector space attributes which can be represented as a maximal term to reduce the matrices space, which can be used to other vanish some matrix term, or reduce the matrix term which can be used. This is called ideals of the vector space. which can be represented by the linear map with maximal term, because there should be some maximal term. The maximal term means after that there is no any more ideal which can be used to reduce the vector space. So here is the ideal is used, which is also supports some isomorphism properties. Here it is showing that the tensor product supports isomorphism properties with some linear bilinear map, which is also supported by the vector space with some linearity dependency. So I have already discussed the this is the whole map, means the whole vector space. And if we use the linear term, means the quotient using the subspace of this map, this is the maximal term of the tensor, which can represent the ideals in maximal cases. This is the C naught gate. C naught gate is basically used for entanglement properties. This is the 0 0 0 0 1 1 0 1 0 1 0 1 1. This is the input and output of a means complementary output. Here the 1 0 gives 1 1 and 1 1 gives 1 0. This is I'm discussing because the understanding of the entanglement property. So what is entanglement? Entanglement is yeah, entanglement is basically the correlation between two states of a superposition with some quantum superposition with some quantum bit, and it is represented by C naught gate. So here I am showing that if we use the Hadamard gate, this output we received, and where the leading term is zero. With this application, this is the zero leading term because the input is zero. So if we represent in Hadamard this input, so this type of output we get where zero is leading. So if we multiply this is zero k 0 0 and 1 0. So if we then apply the C naught gate, we can found the output is in means changing here with some correlation. Like if we use the C naught gate, the Hadamard gate output like 0 0, it is remain same as the leading term is 0, but while we give 1 0, it is changed from as it is leading is 0, so it is complementary 1, so it is changing from 1 0 to 1 1. So and in this case also this is also a leading 1 0 term, so it is 0 0, so it remains 0 because it is 0 leading, so it is remains 0, but while it is coming 1, it is also changing. So this correlation is called the entanglement term. It supports the reversibility property. So now we are going to conic variety. What is conic variety? Conic section varieties. Conic section I have already discussed. The conic section is also called the quadratic curve. Is a curve obtained from the conic surface intersecting by a plane or by a homogeneous polynomial cases to cut the plane. There are three types of hyperbola of the conic section: hyperbola, parabola, ellipse. Basically, ellipse is the closed curve. So the plane that passes to the vertex of the cone, which intersect the cone as a point or a line or a pair of intersecting line, means the cut section is called the degenerate conics. But our consideration is non-degeneracy. Non-degeneracy means imposed a condition on the vector space or the conic space. So we have to consider the non-degeneracy in case of conic section. So the non-degeneracy can be imposed in a conic section using some determinant or the determinant of the or discriminant of the matrix, where the determinants of the matrix cannot be zero. This is a condition or degeneracy condition. If we impose this condition into this matrix, here I am showing that this is a matrix comes from this linear equation. then if it is not zero, means determinant is not zero, this we import this condition due to non-degeneracy, and there are several other conditions which generates the nature of conic sections. Eclipse is one of the closed section. The non-degeneracy is supported by a conic section with some imposed rules or restricting some feasible term to limited the space, means this is the concept of some closed curve or some closed curve or closed vector space to minimize the space of the vector, means the Hilbert space. So what is affine space? Affine space is basically considered to parallel space. Here, I'm giving an example where two planes P1 basically representing the green one, which is the basis plane, and P2 is the other plane, which is basically follows the same geographical structure of the plane P1. P2 is here is the P2 is the upper layer, and P1 is the lower layer. P1 is basically the real vector space of some real application like R3 here, sub vector space, which is basically the subvectors R3 XYZ, which intersects the zero coordinate. This is the main space, and P2 is the subspace or subvector space, which is geometrically identity, which has geometrical identity, means P1 and P2 shapes are the same geometry. They are almost identical, but the coordinates are not identical. We have to if we want to translate the P2 to P1, we have to done some translation to do these things using some tensor product. Here it is defining that if we want to implement the P2 to P1, then we have to do some tensor representation with some inverse term, so that it can be work with the same coordinate of the P1. But they are geometrically the same, follows the same geometry and almost identical. So the space which is identical to P1 means P2 is called the affine space of vector, means it contains the vectors with the same structure of P1, and it can also be considered with some translation. So this is the affine space. Affine space is basically work with Gyrosky topology is basically work with this affine space, which basically supports a closed field of vector. Like here, K is a field of vector, and among them A is A is a point of this field. So there is some affine space with some values A1 to An, where AI is belongs to this field. K can be real, or K can be complex field. Gyrosky topology uses some vanishing points of polynomials. So if we cut some affine space with some points like A1 to An, which is basically a closed which is basically a subspace of a closed field K. Gyrosky topology tells that there are some ideals, means some polynomial term x minus means x minus a1, where x is the some polynomial term with of a function. These are the ideals of a polynomial application x minus a1 and x minus an. This is the term of polynomial. The nth term of every polynomial has vanishes, and using the Gyrosky topology. This basically reduce the spaces of a closed field which we can consider to reduce the application of any affine space. Of a Affine space can be considered as a like view of a database, where we can take the subspace of this of a database like a view. So affine space, we are using like a subset of a vector space with same structure, where some vanishing points are there, and using this vanishing point, the end term of the polynomial is vanishing, means the matrix term is vanishing, so it reduces the vector space. I have already discussed this one. These are the polynomials, and these are the means points, and using the end term of this vanishes the vector space. So in affine algebra solution, the field K of the system of the polynomial equation, these are the polynomials, where these are the polynomials, and these are the points where the polynomials are vanishes at this in term points. So this property is considered by the Hilbert-Neutral algorithm, which is basically used in this scheme. Hilbert-Neutral algorithm, which is basically used is in a closed space, where the property is used for vanishing term of the polynomial based on some closed space in affine-based application. So there are two terms of neutral jet algorithm. One is weak neutral jet, one is Hilbert's neutral jet algorithm with vanishing sets of points of polynomials. So a weak neutral jet is the old term. It denotes some space of ideals, means the polynomial with some vanishing points. Like we have already shown you the x minus ai, the ideals of vanishing term with vanishing points. So this basically consider the vector space with some ideals of vanishing term. So it describes that if the ideal it basically considered and field of K, which is a coarse closed field, and R is a polynomial ring with polynomial ring which basically denotes some ideals, where I is denoting the ideals. So it calls that any vector space with some ideals cannot be vector space of ideals is null, means there is no term if means the ideal is the whole polynomial ring, means that the polynomial ring also means contains some constant term and some the ideal term. So the constant term cannot be considered in case of our ideal, means we have to vanish using the vanishing point. So if the whole ring is the ideal, then there is some constant term which cannot vanish. So ideal cannot be the whole ring, it can be the subpart of the ring. So there is a vector space with ideal uh, cannot be the whole ring. So here the ring is the field with x1. This is a polynomial term, the x1. So this denotes the weak neutralization in the algorithm. And Hilbert neutralization is the some update version, means version 2, which is also worked with a closed field K and some polynomial which is polynomial Nathaniel ring polynomial. Sorry, R is a polynomial of Nathaniel ring type. So what is Nathaniel ring? Nathaniel ring of polynomial is considered the some ordering of the polynomial term, means either ascending or descending order. Generally it is in ascending order it is followed. In case of Nathaniel ring generally considered. So Nathaniel ring is basically a polynomial. Nathaniel ring is basically some ideals of polynomial with some ordering. This is in this case, if R is considered a such type of ring with some field with polynomial term x1, so there exists some point a1 to n, which is basically in the field such that uh, M is a matrix term or maximal ideal term which basically consumes the ideals, means x1 minus in x1 to n. That means that if there is a R is a means Nathaniel polynomial ring for ideals of the polynomial, means x1 minus a1 for vanishing term of polynomial, and k is the field of such polynomials x1 x10, then there exists some vanishing points in the field of k where the m is the means m is the uh, uh, maximal ideals, maximal ideals, it is represented at x1 minus a1. There is some term of maximal ideal which can vanish at these points. And another section, it describes if k is any field, then there is a any field, then there is a Nathaniel ring with these fields. If there is some points in this field, then the ideals, these are the ideals form which can be maximal. So this scheme proves these two ways to prove that this application of vanishing term with maximality, means there is no constant term, only the vanishing term, and it supports bilinear mapping with some quotient value, means subset value, which is termed as m. So it is showing that the evaluation map from R to K, here some constant values in the R, but there is no constant value in the K. This is the evaluation, which is the maximal term. The alpha is the constant term, and the constant term is not be considered here. It is only the maximal ideal is considered in the case of evaluation with some maximal term. So evaluation contains some maximal term, reducing the constant term. So it is kinds of subjective. Subjective means if a function supports by a linear mapping with maximality, where x is equal to where the function f denotes the imposing mapping from x to y, where y is the image of the function of domain x. So here the evaluation supports these kinds of subjective terms, subjective applications. This is the proof of the Hilbert-Nathaniel case for degree D polynomial. This supports the maximality term with polynomial for vanishing in the evaluation map. So this is some practical application. Here it is showing that if we take some ring with xyz values, and these are the points 1, 0, 2, then it generates some ring map with some ideals. This is z minus 2. This is the 2 points z minus 2. This is y is 0, so y minus 0, 0, and this is 1, so x minus 1. This is for generate some ideal with some maximality with the ring map. So I'm not going in details. So Hilbert uses follows the affine space of polynomials, and it basically supports the ideals for vanishing term I am already discussed, which are maximal. It is here showing that. So what is homogeneous polynomial? Homogeneous polynomial is a kind of polynomial that follows the structure where p is a polynomial and lambda x1 to xn is the polynomial term, where lambda to the we can represent it as a lambda to the power dp x1 to xn, where we consider lambda as some eigenvalues, and the x1 term is the polynomial with degree d, with the same degree d, which have the same degree. So if we consider a ring and a field, so x1 are the polynomial term of this field, and thus consume the ring. It is generated from the homogeneous polynomial. So it is related to homogeneous polynomial, has a relationship with Nathaniel polynomial. Sorry, Hilbert Nacharzat algorithm, and it basically represents the non-degeneracy from the homogeneous polynomial relationship, that it restricts the vector space to d plus n minus 1 to d. This is the maximum number of vector space for degree d polynomial, homogeneous polynomial. It is from the theory. This is a kinds of non-degeneracy condition and irreducibility condition for maximality using the Hilbert-Nusselt algorithm with homogeneous polynomial, and this concept is used in this scheme. So I'm now going to details in this scheme. So here it is considered an n-dimensional vector space V, which is a vector, which is a whole vector space that can be R or means real or constant, and there is an algebraic variety. This is the X. X is the means the collection of conic varieties by the polynomial f to fp is given by x is equal to the x. These are the polynomial term. Those are vanishing at 0 point. Sorry, those are vanishing at the point, some points. The X is basically a cut variety of ideals, cut of varieties of ideals of polynomial where they are vanishings. So the problem of finding the given the this is the x, the variety of the conic variety of some ideal terms of cutting by the polynomial, and there is a linear subspace U which is specified by the U, which is also a subspace of the V. So the conic variety is basically cut by this subspace. So if we intersect, so conic variety are the cut by the homogeneous polynomial of degree d. So if we intersect, sorry, one thing I have to consider that this type of the problem is NP hard, because the conic variety consumes some ideality with some broader term, means in the high level matrices. So we have to reduce it into a singular polynomial term so that there is a maximal. It became in a maximal term in linear map, so that it can produce the vanishing points for polynomials. Vanishing term for tensor decomposition procedure, so that it can be reduced to rank 1 matrix to mitigate the chance of NP-hard kinds of problems, and we ensure that it is can be solved in polynomial time. So in this case, author considered the problem 1, where the subspace, the U is the subspace of a generic subspace U, is cut by the which basically subspace is cut along with the intersection of the conic varieties by the which is conic varieties cut by the polynomial degree d f1 to fp. Yeah, if we can certify that there is a intersection between the generic space and the conic variety is 0, that means there the maximality term has reached, and there is no more ideals for the maximizing the tensor decomposition using the vanishing term, so that the maximality has reached. So there is the this is the maximal means term has reached, means the rank 1 matrix or polynomial term has reached. There is no more subspace of this in this vector space, else there is a non-zero point vector, non-zero points of vector in the intersection, like this is considered as V, and we have to decompose this tensor using some simultaneous diagonalization procedure to make it is in a rank 1 matrix or in polynomial linear term. So the V can be a NP-hard problem. So we have to decompose it. If we consider the V is an N1 cross N2 matrix, uh, then we have to form it as a rank one term. So there is a theory. If a homogeneous polynomial of degree 2, which basically determines all 2 cross 2 matrix, then it can consume the rank 1 matrix form. So this is in general term that if a set of matrix of R, this is the rank of this matrix, then there is a determinant variety cut of polynomial of degree R plus 2, means that if there is a n1 cross n2 matrix, then there is a polynomial cut n. Sorry, I'm giving a simple example. uh, if there is a 2 cross 2 matrix with polynomial degree 2, then we can reduce the matrix using some simultaneous decomposition procedure with a rank 1 matrix. This is the simple term here tell to decompose this V. So here it is telling that the rank 1 matrix we have to follow to reduce the NP-hard problem. So we have cut the conic section or consider the conic section as n cross 2 matrix. This is denoted as S, which is a subpart of the rank of the whole vector. This is R. So here we are restricting the R using the term I have already told that from the from the homogeneous polynomial application, which we have restrict the whole vector space size to this one from the application of the means homogeneous polynomial. This is the theory comes from the homogeneous polynomial. So our motto is to cut two section of the whole vector space V, where the cut X is the subspace is denoted by S. S is the subspace of the whole vector size of rank R, and remaining the size R minus S is the general variety U. So this is the remaining one. So here S is the 0 to it can be 0 to R. So elements that contains the intersecting conic variety elements, and U are the generic elements of linear term. So the algorithm one certifies that if the intersection is 0 with some n to the power d time algorithm, the algorithm is running this time because we have d d rank homogeneous polynomial, so it runs up to n to the power order of d. So if the intersection is comes 0, then maximality has reached. So we have decomposed our vector space like this: x to the power means s. This is the conic variety subsection, and remaining vector space r minus s, which is denoted here. But the whole vector space R is restricted using some non-degeneracy condition from the homogeneous d-degree polynomial using this term. So whole span X is the V here. The vector space whole span V, here the V which is restricted by R. So if we consider the decomposing the vector V, which we have shown in the algorithm 1, so we have to decompose the V. If the V is a larger term, then we further use the corollary 3, that the linear subspace can be decomposed up to this term, which is also come from the theory of homogeneous polynomial. That also run n1 n2 to the power order of 1 time, because there is a n1 cross n2 matrix which we have to be decomposed for the term where the u cross x1 is not 0. So we have to decompose the vector v, which already we have shown in the previous slide, like here the intersection sorry, the for the first, sorry, this one, yeah, sorry, this one, for the, if there is no zero, that we have to decompose the V. So we are decomposing the V with restricting the non-degeneracy vector space with this size. In this case, Zaideski is concept is used for the closed circuit, where these are the curves of the closed circuit, which is we can consider this is irreducible because they are the maximized term. So Zaideski topology consider the irreducible component in a closed circuit, which concept we have used here. And another is non-degeneracy, because we have restricted our span of x to some kinds of vector space size restriction using homogeneous polynomial with some vanishing term. So this algorithm use simultaneous diagonalizes algorithm for decompose the term. It use Fuvie algorithm if the if some situation with more complexity come for tensor decomposition in fourth order, then we impose Fuvie algorithm to decompose this application other than using the simultaneous diagonalization procedure. And it used the Zaideski topology for irreducible component and not non-degeneracy. So this is the simultaneous diagonalization algorithm where the vector space is decomposed for the tensor decomposition using some eigenvalues. The eigenvalues is the subspace of the vector, and this generates the vector space v1 to vn with some vector space like which generates the vector space with some vector eigenvectors, which is w. Here we are denoting as w, where it is considered the eigenvalues are not repeatable term. If it is repeatable, then it is failed. Otherwise, we can consider if there is any inverse term of this application. If it is some inverse term, then it is supports the homomorphism, means isomorphism properties of the eigenvalues. So if it is the inverse term, then we can consider a vector space w1 to wr with some eigenvalues with inverse term, and this is considered as WA, and VA are the eigenvalues with constant term. We can decompose the matrix with this form matrix decomposition with simultaneous diagonalization matrices with some eigenvalues. So to reduce the matrix term. So here it is showing that the eigenvalues of inverse term consider the isomorphism, which supports the maximality condition for bilinear mapping. Here is the algorithm 1, which basically so using the simultaneous diagonalization algorithm, this authors proposed one algorithm 1. Algorithm 1 is basically we have already discussed that suppose two varieties. One is S, which is curved varieties, which is formed by curved by degree D polynomial f1 to fp, where a basis u1 to ur is considered for linear subspace u, which is a subspace of the whole vector, and there is a conic variety x, which is also a subspace of the whole vector. So x is S represented by S, and the remaining u is represented by r minus s. We have already shown this is so where the conic variety supports a span of some cut of the by the polynomial, which is the ideal. Id is the ideal, which also supports the isomorphism properties of the span of the vector. Isomorphism properties that basically consume some points, vanishing points. So the if there is a we have done any cross section of this cross section with ideals with the homogeneous polynomial with basis. So if we get 0, then it is the maximal term has reached. Otherwise, if we have to further decompose the vector V using orthogonal matrices, using the orthogonal simultaneous decomposition matrices. Here it is using where the V and the d to the power d minus 1, because we are decomposing the matrices in a eigenvalues term, z1 and v1. This is eigenvalues term. and if in any case the conic variety S is greater than R, then the output will fail. When this does not support non-degeneracy condition, so it fails. So algorithm 2 checks if is really the intersection between U and X is 0 or not. If it is 0, that means maximally term has reached. Means if it is 0, that confirms that the maximality term has reached. So there is no more maximality. So it confirms that the algorithm 1 is working perfectly. Otherwise, it generates output as failed. So this is the overall application of this term, the overall application of this algorithm. It says that if we take a degree polynomial with a cut variety of that follows the isomorphism property for the maximal ideals with maximal ideals ID that is generated from the cut by the degree d polynomial. So this suppose the means the isomorphism property which is cut by the x, which is a subset of the vector, and the basis u1 for linear subspace u to the v. So there is some basis of points which is basically intersected by the polynomials by of the span of the polynomials which generates the ideals where the spans of the ideals are the polynomials. The generic space supports some isomorphism property from the maximal term of the ideals using the map. Here, if we intersect the general term u with the span with the degree d polynomial with the identity generated by the cut section, if there is 0, that means that maximality term has reached. Otherwise, we have to decompose the points. Here, if the maximal condition is not reached, then simultaneous diagonalization is applied for the tensor D vector. Tensor D vector. This is a vector which does not follow the cross maximality term, so we have to decompose into a linear term or polynomial term to make it is a linear application from the higher order term. Means it can be NP-hard problem. So it is done. So if it does not follow, then the output becomes a fail. So the key points I have already discussed, that it tries to solve the several entanglements techniques, R entangle, complete entangle, DT entanglement, and it tries to solve the NP-hard problem into a linear term or polynomial term using some matrix decomposition or tensor decomposition methodologies. So this is a basic illustration of this term. The same way we have illustrating this as an example. Mm, I have already shown the strength of this means application. That is basically you consider several entanglement, and it's basically decompose some conic varieties with some linear term. We basically consider the NP-hard problems and solve it is in a linear term for the vector space based application in case of entanglement and other quantum related terms. So it is very much applicable for quantum based applications where variety space varieties are considered for the and the entanglement for the entanglement and other terms also using Hilbert-Neutral algorithm for the closed vector space. What are the weakness? This algorithm does not consider a situation for the long distance communication in case of vector space based application in a closed space or in an open space like quantum teleportation. Quantum teleportation is a scheme where qubit from the sender to receiver is communicated using to classical bit, and the opposite scheme is called superdense coding, where the classical bit is information is transmitting by a smaller number of qubit. So in these cases, this application is not still considered. So we want to work on this limitation of this scheme and try to maximize this application for such kinds of long distance communication for vector space based applications in close term, with this is also a NP-hard problem. We want to solve it in polynomial time also. So in conclusion, this is a very good application which can form the NP-hard problem into linear term using tensor decomposition to recover the high order tensor to a polynomial time algorithm. So these are the references, and thank you.